Welcome this week. So far, we have looked at inductive learning. Inductive learning means that we have observations, and from these observations, we derive rules. And with these rules, we can then classify or predict a value. When we do transductive learning, we do not take the training examples as a means to learn rules, at least not primarily, but we directly use the training examples in order to classify other data. And in that sense, k-nearest neighbor also is a transductive approach. Transductive, sometimes some people argue that transductive learning is more natural case than inductive learning, because they argue that, well, we as humans, we don't really learn general rules of how does a duck look like, or a pigeon or whatever other kind of bird. We rather learn from some training examples the way a duck or a pigeon or some other bird looks like, and work directly with these training examples. Maybe we don't use all our experiences about how a pigeon looks like. We may have seen thousands of pigeons, right, or more. We don't remember all of them like KNN does, but we directly use such images of how pigeons look like in order to classify other objects as pigeons. And this is the idea that underlies transductive learning. That we have training data, but that, and this is then different, we also have test data. So the idea is that we do not only use the training data to create a rule, but we already have test data, and we use this test data actively in order to generate experiences. So it's a bit like you go on a safari in some neighborhood that you don't know, whether that's some forest that you have not been to where there are some birds, or whether that's maybe some prairie where you haven't been to and there are some other animals you haven't seen, whatever. And immediately you recognize the similarities, even when you don't know the explicit category. So we can use test data, and then the learning happens also specifically for the given test cases. And then it depends on the exact algorithm, not only for these test cases, but also for further ones. But this is also a use case that we have in different applications. For example, when I have a spam classifier. So I have my hundreds of thousands of emails, it might be by now, and I have flagged some of them as spam. And I have flagged other ones explicitly as not spam. And of course, I have many more messages that are not flagged at all. So this is very natural. I don't even want to include all of them. And what I will show you in a minute is that it's very useful to have the test data available. It improves the accuracy of the classifier when you do not only have the training examples, but when you also have the test examples available. Yeah, news recommender would be another example, or document reorganization would be another example. So let's look at support vector machines. So usually what we do is we have positive examples and we have negative examples. And when we look at transductive learning with support vector machines, and by the way, support vector machines is just one example of how you can do transductive learning. I mean, you can think about other paradigms and consider how you can do transductive learning with other paradigms. But we do it here with support vector machines. So then these dots here, they stand for unclassified data. Well, let's say here you have a few spam examples and a few non-spam examples, and the round dots here, these stand for messages, emails that are not classified. Now, what would happen if we only considered the pluses and the minuses? Maybe we would have a line like this dashed line here as our support, as our separating hyperplane. It's not optimized for that, so maybe it's not quite the perfect one, but let's just assume it for the sake of the argument. And now, what happens when you take this line and you classify all the dots, and then you assume that this hyperplane was correct? Now you would have new information. You would have the information that this must be negative, this must be positive, etc. So when you use your training examples to build your separating hyperplane, what you get is new training examples. And when you do this, what do you end up with? Well, you end up with a new training set. And when you use then this new training set and you provide this again, you would get to an improved or at least to a changed representation. So obviously, if now this becomes negative, then this is a very short distance, and it might be better if you actually would move this hyperplane. Now, a naive approach might say, let's look at every possible hyperplane. And for every hyperplane, classify the dots. So the dots are here described with this asterisk. And let's assume then that for a hyperplane, these unknown dots are classified. Then compute the loss. What would happen? And that would, of course, also mean that you would use this hyperplane, which is solid. And what you would find is, okay, you would have a really nice set of negative examples, a really nice set of positive examples, and a really good support vectors that are quite far away from this hyperplane, much better than if you would have taken this dashed line. This is nothing else than an optimization, a loss function. And this loss function, the first component, this is the regularization of trying to minimize the size of the vector. Then you have your one condition that we saw already last time, where you look at these zetas, and these zetas are to be minimized under the side condition that the constraints must be fulfilled. So here, in particular, the classification by your function times the class plus 1 or minus 1 must be, in general, larger than 1, or if you have slack variables, larger than 1 minus the slack variable. And now comes this third component, which says, now we assume that we have classified everything for any possible hyperplane. And that, of course, would mean that we have also a classification and a corresponding loss for these asterisk dots. And that's where this further loss comes into play. And now you have to consider that in usual circumstances, like 100,000 emails, you may have maybe 1,000 ones that are classified, but the majority are actually not classified. So this becomes a really important factor, of course, underlying the same constraints. Now, I don't go into here how to do this operationally. I mean, there is this paper, if you're interested in that, that also shows you how to do this efficiently. But that's not so much my point here, because I really want to familiarize yourself just with the thought that you can, well, first, that there is the thing called transactive learning. Second, that Maybe if you have a particular challenge, you want to reformulate your machine learning challenge. And then it is always a good idea to start first with a naive approach. Again, that's a typical way to think like a computer scientist, to say, that happens a lot, all over the place. You even formulate initially a condition that's not computable because it's too intractable, but you have a very clear goal, a very clear objective, and then you separate the thinking about how can I achieve this efficiently, maybe exactly, or maybe just by approximation. Right? And so here you have this part where you say, okay, that would be wonderful if I could do it like this, and I just test all possible hyperplanes, and from all possible hyperplanes, I take the one that gives me the smallest loss, and the loss would be this small extension of the loss that I have considered before. And once I'm so far, I have this very cool idea, then I consider separately how to approach this by some algorithm that is tractable. And just to give you the result without showing the tractable algorithm, so here are some examples, some test documents from the Reuters dataset. Reuters is one of these default datasets that people have played around a lot. Some 10,000, 15,000 documents. We also used that in the past. And they come with some classification. And well, here below you have some naive Bayes approach. And then you have the default support vector machine. And on the x-axis you have the number of examples in your training set. It's not exactly a linear scale here, what you see, because between 17 and 26 there's just 9 difference, but then there's 20 difference, so it's a little bit like a logarithmic scale, not exactly. And what you see with the number of examples growing in the training set, the support vector machine, which is the second line, which is the line here, gets better and better and better, and of course at some point increasing the number of examples in your training data set doesn't improve the situation anymore. And what happens if you use transductive learning for the transductive setting? You take this 3,300 test documents approximately, and you take 17 documents that are classified. And immediately you are in a range, I think that was average precision recall break-even point. So you look for precision and recall, and you try to determine where is precision as large as recall. You change the hyperparameters a bit. And what you find here is that you are immediately with 17 examples at a point that would take you something like 88 examples approximately with the conventional technique. And as you increase the number of training samples, you always stay ahead above the conventional support vector machine. So having this knowledge about your test data and knowing how the data is distributed over your data space helps you to make a better decision as to how to put the hyperplane. This also runs under the title semi-supervised learning. Supervised because you use the training data as your supervision, but semi-supervised because the test data is not really supervised data, it's really data that adds further information about the spread, the shape of your distribution. Another diagram. Here one can look at the examples in the test set. Of course, for naive Bayes and support vector machines, the number of examples in the test set does not influence the performance. But for the transductive support vector machine, the number of examples in the test set up to a point of about well, maybe 500 or so, improves the classifier. And here specifically, this was true for 17 training documents. So a really sparse sample where only very little manual work is required. Because, I mean, classifying documents, yeah? You know this yourself when you classify email, and that's work, yeah? That's what people want to avoid. Okay. So much for transductive learning. What I want you to show in one last slide in this section is work which approaches yet another problem, not related to transductive learning, but one to learning with multiple labels. So when you have, for example, images, it's easy to imagine, you might want to provide labels, say this is a duck, this is a bird, this is a vertebrate, or you might say this is a husky and a dog, and the dog is some sort of a mammal, etc. So you have a taxonomy, and some of the taxonomies can even be put together. You could say you have some pet, and a husky could be a pet. Maybe a duck, I'm not sure whether that could be a pet, but you could have another kind of taxonomy about how animals are treated as pets, or rather as a livestock, or as neither. Yeah? And you can define that some of these different categories are compatible with each other. For example, something can be a pet and a dog, but you cannot have something which is a cat and a dog at the same time. At least so far, genetic engineering has not moved far enough to do that. Yeah, you can have sheep and goats. Yeah, in German that's a Ziege. That was genetically engineered, but no cats and dogs so far have been possible in one category. So, this is an approach by one of our PhD students that we published. And here the idea was also to use separating hyperplanes. I have to be clear, we didn't use SVM, but hyperbolic logistic regression. So what is the idea here? Here it's mentioned with hyperbolic already. Namely, you put your objects, you learn your objects with a neural network and put this on such a Poincaré ball. In the easiest case, a Poincaré ball is just a disk. So this is a space which is cut out from the, for example, let me describe it with two-dimensional case, but actually we were not limited to two dimensions. With a two-dimensional case, one would use this disk, and all the object representations lie on this disk. But this Poincaré disk in a 2D case is a hyperbolic space, or a hyperbolic cutout of the 3 dimensions. And when I have talked so far to you, I always mentioned Euclidean space. And in Euclidean space, you have certain geometric properties. For example, you have the geometric property that if I draw a triangle on the blackboard, the 3 angles together add up to 180 degrees. Yeah? But if I use a different geometry, for example, a spherical geometry, so if you imagine that this is the Earth, then if we move around on the Earth, then, for example, this is the North Pole, and we define triangles there, this is the equator, then if I use these 3 angles of this triangle, which lies flat on the surface of the Earth, then these 3 angles add to more than 180 degrees. And you can also have So I mean, this geometry of the Earth, this is warped in comparison, when you define the geometry in comparison to this flat triangle here. And you can also define geometries like on the Poincaré disk, and there the sum of angles in a triangle can be below 180 degrees. And in particular, on the Poincaré disk, one defines a metric, so distances. And when I draw a tree with the same distances, then maybe this could roughly look like this. And this distance is as large as this distance. So when I depict this in this Euclidean space, they look like different distances. In fact, when I move away from the center point, then these distances, as I move away, as I do a tree, grow exponentially. Whereas if I draw a tree on Euclidean space, I have always the problem that these distances do not grow exponentially when I move away with same length branches, and I always have the problem in such an ancestry tree that I never have enough space. So on such a Poincaré disk, since the metrics are different, I have a lot of space as I get closer and closer to this edge of this Poincaré disk. And actually, that is an edge that's actually just due to our two-dimensional visualization, because any point on this Poincaré disk can be brought into the middle, and it's just an artifact of our visualization that it looks as if these distances here are smaller. In the actual metrics of this other space, they are as large as the distances here. So what is now the advantage? Since I have different kind of metrics, I have different kind of hyperplanes. And the hyperplanes are visualized by intersection with other circles. So this here is a hyperplane. And such a hyperplane can have points on the right side or on the left side. This here is also an hyperplane. This is also an intersection of such an external ball with this Poincaré disk. And again, I can have points on the right side or on the left side. And now, as all these things are, from a Euclidean point of view, warped, I can nest these hyperplanes into each other. So this orange ball is nested into this green ball. And so I can associate, let's say, the husky inside this orange ball, inside the dog ball, which is a superordinate label, dog being more general than husky. And of course, these things can also intersect each other, so these two are disjoint. Yeah, so this would be, for example, a dog, and this would be the cat, and then according to these two hyperplanes, I could separate a dog area from a cat area, which is not something which I could do directly with support vector machines. I mean, unless I use a kernel trick. With the kernel trick, I can do other kind of stuffs. And so what Bo did, the PhD student, he formulated this multiple label nesting by constraints, and then defined these hyperplanes in this hyperbolic Poincaré disk. And again, so it was a new problem. Well, not completely new. People looked at multi-label classification before, but he had these constraints about things being separate or things being able to be nested, and solved this. And so far with hyperbolic logistic regression, maybe hyperbolic SVM would be even better. Hyperbolic SVM also exists, so maybe that would be a nice bachelor project or other kind of research project to pursue. To test this out and compare. Okay, this is not. So this slide is not for the exam or anything. It's just to give you a bit of the flavor that you can redefine some of the machine learning problems you encounter. Define a loss function. Look at how to solve this loss function, and you can play around with things. Here, Bo played around with the geometry. And actually, he's not the only one. So hyperbolic geometry is much used by many people. And sometimes one also uses spherical geometry, like this, the surface of Earth's globe, as a kind of a geometry. And the rules, of course, change how one computes distances under such circumstances. Good. Questions to support vector machines in general, or to this last set of slides I showed you today? Not at this point, it seems. Okay, then we start with neural networks. And the first thing I like to start with neural networks is some demystification. I mean, still people enter this whole area and bring a lot of mystique to artificial neural networks being very close to biological neural networks. And this mystique is sometimes helped even by very prominent courses. So for example, here is some MIT courseware by Patrick Winston, a super popular and successful AI researcher. And I have to say that, half of what he says here in this first few recordings of his course is correct, but then also half of what he says is nonsense. At least it's nonsense if you would take it literally. So what does he explain? And what he explains is that artificial neural networks are indeed motivated by researchers who looked at biological neural networks. And what are biological neural networks? He makes this very nice drawing, which is very nice. So this is a brain cell. A brain cell has a core, and a brain cell has this dendritic tree, and this dendritic tree receives information from other brain cells. And then this dendritic tree and this core consumes this signal and forwards this signal along its axon, so along this long connection, and has some further synapses at the end, so maybe here, several of these. And then you have here the synapses, and you have this synaptic gap. So this is an enlargement of the situation here. You have here this end, you have a synapsis, you have a synaptic gap to the next dendrite. And here is then the next brain cell. And the propagation of information along this axon happens by chemicals changing their orientation. So there's always the question, is there positive or negative Ladung? I just didn't hear the word acoustically, that's all. I'm sure you did it correctly, but could you please speak it out loud? Charge, yeah. Okay, so I didn't understand the word charge. Yeah, Ladung is so this charge, and it's either positive on the outside and inside negative, or it's then reversed by this chemical process. And this is a very speedy process along propagating this information along this axon. And then there comes this synaptic gap, and here some chemicals, these neurotransmitters, are emitted from the synapses. And these neurotransmitters, they bridge this synaptic gap and are observed by this dendritic tree of the other neuron. And then again, this next neuron takes this input, computes some output, and forwards that again. Yeah, so this is what's basically happening. That's what Patrick Winston explains correctly. And now the core idea of the artificial neural network is that we have vectors, and a vector consists of different values, x1, x2, up to xn. In the simplest case, that would be just values of either 0 or 1. It could, of course, be also values in between. And you take these values and you have some sort of combination of these values. And this, what we do in artificial neural networks is we weigh these individual inputs. We weigh x1, we weigh xn, and we weigh them possibly differently. We sum up these weighted values, and we do some kind of decision function, some so-called activation function. And then we forward a signal, or we don't, or maybe a strong signal or less signal. And this is basically the understanding of biological neural networks from the 50s of the last century. This is where the mimicking of the biological idea almost ends. Namely, there is a problem. Initially, people thought it was like that, but it is not like that. And indeed, the problem is such a biological neuron has to bridge this synaptic gap. And once these neurotransmitters are emitted, it takes some time until they are cleaned again, and a new signal can be promoted. And so at the biological scale, this takes about 100 milliseconds to emit them, and then also to be such that the neuron is ready for a new signal. And if you think in terms of how fast you can receive something and record something, and you test how fast people can be, it's in this order of 100 milliseconds that you can even process some information. But with a 100 millisecond reaction of a single neuron, you couldn't really walk. You would just fall over all the time. Because, I mean, it's not just one neuron which is involved, right? So, actually, what these neurons do is they have some temporal encoding. It does not only matter how fast the individual neuron reacts, but it depends on what the time scale is of neurons happening in parallel or with some lag. So basically, what is the wonder of the biological brain is that with a rather slow system, it comes up with encoding issues that happen at 1 millisecond scale, which is really fascinating. And you can try to do this with temporal coding, try to understand it with temporal coding or with differential equations. And there have been proposals to rebuild artificial neural networks that use these principles, like spiking neural network, where the question whether something is classified as a cat or a dog is not just happening by weighing inputs and making a decision, and this may be several times, but where the temporal coding plays a role. And there are books about that, but unfortunately, we haven't really understood very well how this all works. We have not been very successful as research community to use that. Maybe we'll be in the future, I don't know. Maybe you'll find a new solution. But so far, we haven't been there were books about this. Here's some example. And Chris Bishop is a major researcher at Microsoft and so on. So there were really significant efforts to understand this. And I'm sure there are still people working on this topic. There are also some very limited approaches. For example, there is such a biological worm, I think it is, C. elegans. And the C. elegans has some 60 or 70 neurons and is able to fully steer the body with just these 69, I think it was, but I'm not fully sure, 68 neurons. Is fully able, this worm, to steer and control everything of his body, which is enormous if you think of it. And people have looked at how to use differential equations in order to simulate this neural network of this simple worm. And this works, but of course it's very far away from the kind of high-level understanding or problem solving that we try to achieve with our artificial neural networks. And so there's a lot of space. The message from my point, however, is we really do not take that much inspiration from biology. We do some. For example, we'll learn about convolutional neural networks, and there are some overlaps between the biological original and the way we define these artificial neural networks. But most of the time, it is really what we do is a technological solution. And if we maybe at some point find a better one, then we could make even much more progress with AI than we do right now. The other story, of course, is you should always remain critical about what people tell you, yeah, even if they're very prestigious and very respected and very successful. I mean, Patrick Winston is like a super researcher from MIT, has researched AI for 50 years or so. Maybe he's now retired or dead, I don't know, but Coursera is still around, and sometimes people also tell me, look here, they claim this. And of course, I will do mistakes, so please forgive me for that. But also be critical about what other kind of impressions you're provided with, and definitely biological neural networks are quite far away from our artificial neural networks. But sometimes inspiration is, of course, good, and inspiration does not necessarily mean that you have a one-to-one copy. Yeah, that is, of course, the other thing. Okay, before we go into neural networks, let me first give you a very brief reminder about logistic regression. You remember we had for logistic regression a linear function. The linear function was z equals x transpose beta. So basically beta weighs the inputs. And then we have this nonlinear activation function, which says y is e to the power z divided by 1 plus e to the power z, where z is this weighted input. And yeah, in this simple case of one input, this is just this kind of activation function that takes an input from minus infinity to some input between minus infinity and plus infinity and turns it into some input between minus 1 and 1, or here between 0 and 1. And we have a loss function which consists of cross entropy and some regularization. So with regularization we want to have small weights. But otherwise it's primarily cross entropy, where we look at how well do we model the probabilities for our classes with the indication that an object belongs to a particular class. And we can do this with 2 classes. We can also do this with several classes. And this changes things here only very little. And we did solving by gradient descent. Well, that's it. We have our loss function. Now we minimize our loss by changing the weights, computing the how the weights should be changed, how the beta should be changed, such that the loss becomes smaller. And we can do a few observations about this construct when we have the probability that our x, given our x, this belongs to the one class or the other class. Then, of course, the two probabilities must sum up to 1. That's given by one class has this probability as indicated with a black line, depending on this input of x transpose beta. And the other probability is this green line. And now there was all this proposal existing with some perceptron-like mechanism. And then, I don't recall now who did it, but someone said, this simple approach here, well, what was described here, linear weighting plus some activation function, yeah, that was advertised first as like, this is how we should do learning, which is what we can do with logistic regression, for example. We can use other activation functions, of course. And then someone came and said, but what about XOR, the XOR problem? Can we classify objects if the class is defined by XOR? What does this mean? Let's say an object has two attributes, x1, and the values are either 0 or 1, and x2, and the values are either 0 and 1. Whatever these values stand for, doesn't matter. And the value of the class is then described by the XOR. So 0 and 0 leads to the class 0, 1 and 1 leads to the class 0, and the other combinations lead to the class 1. You all know XOR as a Boolean circuit. It's a very simple thing. And now the question is, if we have objects like this, can we train a classifier to classify objects correspondingly? And the answer is no, we can't. Because what we do with logistic regression is we always establish a hyperplane in Euclidean space. And with a hyperplane Euclidean space, you can try to look at what kind of separating line allows you to put the zeros into one side of the hyperplane and the ones onto the other side of the hyperplane, and this doesn't work. Yeah, we saw this actually also before. That was one reason for us to actually use the kernel trick. And we can look at the odds, yeah, the log odds. So we look at the probability for the one class, compare it to the probability for the other class. And when we use the logarithm of that, this is nothing else than, well, this probability for the one class, probability for the other class. If we compute this is nothing else than the logarithm of e to the power z, where z is x transpose beta, and the logarithm of that, logarithm and the exponent, they cancel each other out. So the odds where they are equal, where this is 1, is exactly the situation where x transpose beta equals 0. But if the logarithm is 1, the value of the logarithm is 0. This is where x transpose beta forms a line. And x transpose beta, the separating hyperplane, could be a line like this. This is not a straight line, really. Okay, my problem. But you see, no matter how you try to arrange a straight line, you will not be able to put the things on one side. Okay. You try it at home, you'll do it better than I do it here. So, yeah, how can we now separate things non-linearly, not with a single artificial neuron as we now tried? Kernelization is one possibility, or, and that's what is done for neural networks, we compose nonlinear functions. We put several of these functions in a row. And that brings us to the simplest kind of neural networks, namely feed-forward networks with different kinds of activation functions. So what we do then is we define different layers. We define different layers. So let's assume we have a first layer. So that's a function that takes a vector and returns a vector. A second layer, the same thing, and a third layer. And the third layer is the output layer that gives us our prediction, our y hat. And then we provide an input, our x, and the overall function is defined by taking this input to the first layer. The first layer provides some output, gives that to the second layer. The second layer takes this vector input, consumes it, produces a new output, gives it to the third layer, and then eventually we have some targeted output. So this would be a three-layer network where we repeat this application of summation and activation functions several times. We can have just one such neuron per layer, but we can also have a whole number of such neurons per layer. And now if we, for example, take a very simple example, this is the input layer, the values that we provide in. We have one hidden layer and we have one output layer. So this would just be two layers basically here. Then we can find a solution for our XOR problem by nesting two functions that have this shape of having weighted sums and an activation function. And what we do is we also draw these networks by saying how is the input forwarded. Each artificial neuron has such a kind of a summing and weighting and activation, and then forwarding to the next layer, and there we have similar performance. And so this layer here is described by F1, and this layer here is described by F2. And when I now look at what degrees of freedom I have, then I have a weight matrix. The weight matrix describes how each of these two neurons weights the corresponding inputs. So these are for two neurons, two inputs gives 4 possibilities, 2 times 2. So this is a weight matrix of size 2 times 2. Then we describe a vector where some offset is added to the summation, and then we have a similar thing, but here we only have one neuron, so we only have a weight vector and again some offset. So F1 gives us some vector of hidden values. F2 takes this vector of hidden values and gives us the output. And the overall is then composed. Okay, now what would happen if we don't have an activation function, but if we compose linear functions? In the case of linear functions, what would we have? We would have that f of x would simply be a weighting with a vector of a weighting of this matrix times our input values, again a vector. If we only had linear functions, then of course the idea in this network would be that we would have input, this would be reweighted, reshaped, and again reweighted. But when I have this composition of functions, of linear functions, I'm free to choose whether I multiply first on the right or whether I decide to multiply on the left. And so I can decide to multiply first on the left, and that means on the left I have a linear modification of my input, and that means a composition of linear functions gives me a linear function. So when I do several linear functions compose that's the same as having just one linear function. So several linear functions don't help me at all in solving the XOR problem. But if I now take something else, namely I have some activation function which is maybe somehow parameterized and or some feature function phi, and I weigh that and I maybe add or subtract some value, and then I describe this. Then with this function I introduce some nonlinearity. When I introduce nonlinearity, I cannot simply put these different layers together. And the question, of course, is what kind of nonlinear function, which I then may weight, do I want to pick? So a core idea is here quite similar to what we did with logistic regression, namely, we define our function phi by saying it's a g x transpose theta or theta I. This is a linear component, and this linear component is provided to a function g, and this function g is picked, but it's nonlinear. We did a similar thing with our logistic regression where we sort of like had our x transpose beta, and that was our set, and that was given to the sigmoid function. Well, of course, we can take the sigmoid function again, defined as before. We can, however, also take other activation functions. A simple one that was defined very late, only in the 90s by Sepp Hochreiter, was the rectified linear unit. The rectified linear unit is a non-linear function. It's 0 for all input values below 0, and then is x for all input values x that are larger than 0. And what we do with this ReLU is, or here it's defined as the maximum between 0 and z, g of z is maximum between 0 and z. It introduces this kind of broken point, and then it continues smoothly. It's non-linear. And I mean, this has some nice properties because it is smooth, it's differentiable, which is nice for our gradient descent that we want to apply later. This is not smooth, or not continuously differentiable at this point, but as I said, as I told you one time before, hitting exactly this particular value 0 is not likely, and even if you do, you can just pick either the gradient from below or the gradient from above. The gradient here is always 1, and the gradient here is always 0. So if you hit exactly 0, you could even just randomly pick between 0 and 1 and just wait for the numerics to play out. There are variations like leaky ReLU always has some value 0.01, for example, never saturates fully. Or you take another nonlinear function, which is just the maximum of several inputs. Or, and that is used. Or you take just the absolute value. The absolute value of some input is also a nonlinear function. Or that's how people started in the 80s. They used tangens hyperbolicus, which has a shape which is a little bit like the sigmoid, but between -1 and 1, if I remember correctly. Radial basal function, which we have used also with linear regression, for example, is yet another one that you could possibly use. The most used today, because of its simplicity, is ReLU. Very efficient to compute, and you need very few arithmetic operations. So now, how does this help us? If we now have our XOR problem, we have our parameters, and now our overall function is the linear part the weight matrix times our input plus some offset vector, and the maximum of the zero vector, and this maximum is applied component-wise. So this weight transpose x plus c is a vector of length 2 for this example. This is a zero vector of length 2, and the maximum is applied on each of the two components individually. So we get a value by computing that, and then we reweight this 2 vector again and add a bias. This is a weight vector of length 2 transposed. This is a vector of length 2. So here we have a scalar product, a dot product of these two vectors, which gives us a value. And to this value, we add another scalar b. And then this should indicate whether we decide for the one class or for the other class. Okay, let's look here at our training data. These are the x's. This is the input of our x's, namely 0, 0, 0, 1, 1, 0, 1, 1. So these are all possible combinations of our attribute values. And then the class, this is just the XOR, right, of the input values. These are the correct class assignments. And then we can go through that. So the weight matrix we can use here is just 1, so we just do a summation. So the weight matrix W transpose X just gives us this 2 times 4 matrix, 0, 1, 1, 2. And we subtract 0 minus 1. So when we subtract that from these results here, we end up with this new 2 times 4 matrix. And then if we apply ReLU in a pointwise manner, we turn all this negative number into 0. And if we then reweight, we get exactly our target. So by this simple introduction of a nonlinear activation function, we are now able to solve this XOR problem. Small hint on the sidelines. XOR, in machine learning, XOR is a very much liked problem to look at corner cases. Yeah, also when I talk about probabilistic machine learning, this other lecture, again, people look at XOR. Can you do XOR problems? Or do you get stuck in some in some corner with your existing algorithms that does not allow you to solve some version of the XOR problem? So what happens is that at this intermediate layer, we compute these H values, the values of our inputs at the hidden layer, that we re-represent now our inputs in this new space. And the new space is some things collapse to 0, other things collapse here at this point. And now in this new space, I find a separating hyperplane. And yeah, that's then what has happened by this nonlinear function. Now, you might ask, how powerful is this whole method? And there is some theory which is rather broad. Namely, the theorem says if we have some phi which maps the real numbers onto the real numbers, which is a non-constant, bounded, and monotonically increasing continuous function. So continuous, so you don't have any jumps in there. Monotonically increasing, you always have values that never become smaller. Bounded, it does not go to infinity. non-constant, it cannot just be the same value all over the input space. And if we have the space of continuous function on this compact interval between 0 and 1 and 0 and 1 to the power m, so it could be an m-dimensional function, then for any epsilon that you pick and any function out of this compact space, there exist some numbers and some parameters such that you can define a function capital F of x, and this function capital F of x is nothing else than some linear input of the x forwarded to this function phi and reweighted such that this capital F of x is less than epsilon away from f of x for all possible x's. So this means nothing else than when you have any of these phi's, including the functions that I showed you, you can on a compact interval approximate any function to arbitrary precision. Of course, the critical point here is this n. You may need a large number of n's. And of course, the smaller you pick your epsilon, the more, the larger the n you will have to have. So the more parameters you will need. This universal approximation theorem is not useful in practice. It takes this very simple shape here, where you basically have one hidden layer, and that's not really what you want in the end. You may require an exponential amount of such parameters, so you would have a very, very broad network, so even with just one hidden layer, in order to approximate your original function f well enough. And this may also not generalize very well, which is what we want. But it at least tells you that there is no architectural constraint to approximating any such continuous function on this compact domain. And so in that sense, we know that when we pursue this approach, we are powerful enough and we can solve our problems. How good they generalize and things like that, that's then a separate question. Of course, this is also, I mean, in linear algebra or with Fourier analysis, cosine transform, etc., you have a bit of similar result, right? That you can recast your original function by reformulating the basis for your function system. And that's what you do. You pick a different basis. So, what is a one-layer feed-forward network? You have linear functions, x transposed, weighted with a weight matrix plus c. You have a nonlinear activation function, which can be anything like ReLU, like sigmoid, like tanh, like radial basis functions, etc. And then you put the function together by reweighting this g, this activation function, which is provided with a linear input of the x's, a linear modification of the x's. And then actually, of course, when we have not, this is for one layer, but if we have several layers, then of course we can give this input again to the next layer, which is treated likewise. Yeah? And of course, if we use this bias by always having x's that give us a 1, then we can also even write this more simply like this. And we would expect that the g also gives us one component with 1, so we can even be more compact with our writing. Now the question, of course, what is the kind of loss function that we look at? And what is the kind of solving strategy that we look at? And one big question that we have to look at is, do we always use such a simple formulation like this one? And the clear answer is no. Yeah? We will modify this for specific problems. And we modify it in order, I mean, this is also called the architecture. With the architecture, we mean how is input modified, forwarded, etc., etc. How many neurons do we have? How are they connected? This is the architecture. And we modify the architecture in order to improve the generalizability of our function and the training of the function, the adaptation to our particular data points. But of course, we still need to look at the specific loss functions and the specific way in which we find our parameters. The generalization of what I just said is given here. So we don't count the input layer. This is just some vector plus this component number 1, which gives us a 1. And oftentimes this x is also described as h indexed by 0. So h being a vector and indexed with 0 for the 0th layer. Then the first layer is nothing else than the activation function of the linear modification of x, or could write h0 here instead. Second layer is the activation function of a linear modification of the previous layer up to the nth layer, which is a linear modification of the previous output values put into the corresponding activation function. And of course, the activation function here always, well, not always, max out was an alternative, but most of the time worked just by looking at the individual components, like 10H, like Rado. They just look at the individual components of the vector they work on. So, design considerations for the architecture are how deep, how wide should the network be, and of course, what are all our weights. And now the whole idea of neural networks is, as we look at them now, of several layers feed-forward networks, was at least in the 80s, it was around broadly already. But people then typically looked at networks of depth 2 or 3, and with increased computational power and much, much larger data set sizes in the zeros and 2010s, then people increased the number of layers. I mean, the more layers you have, the more parameters you need. Yeah? The wider your network is, the more parameters you need. And every parameter adaptation or parameter learning is costs. And of course, it was very important that in the zeros, like late 90s zeros, people learned how to do computing with GPUs. And GPUs became a common good because of video games. Yeah, basically, the gaming industry enabled deep learning, you could say. Yeah? Because without the GPU cards, NVIDIA was basically a company to build GPU cards for video game players. And then they basically allowed all this matrix computation. If you had computer graphics courses of how to compute three-dimensional scenes and visualize them, this is basically all matrix computation. And that, well, existed in the early 90s. Yeah, I was working on some SGI, for example, then to use this matrix processing pipeline. But at that time, it was in the middle 90s, it was mostly still research stuff. And end 90s it became like common good for video games. And that then enabled the scaling to deep learning, because you have to do a lot of matrix multiplications. Okay, and then you see here with more layers for a very simple data set, multi-digit numbers, so handwriting recognition of numbers, there's some default data set, then when you increase the number of layers, you get a higher and higher test accuracy. Of course, I mean, note the scale here. It starts with 92%, that's already very high, and it grows to 95 something percent. So it's the diagram cheats a little bit because the increase is not as dramatic as it looks like. You always have to be careful with reading this, of course, like what is actually on the x and y axis. But still, I mean, if you think in terms of mistakes, of errors that you do, here you would have an error rate of almost 8%, and here you have an error rate of only 5%. So that means if you turn handwriting into actual automatic digits, there's only about half as many digits you would have to correct manually. That's, of course, a good improvement by having more layers. Okay, so now let's have a feed-forward network where we do the simplest thing possible, namely predict a Bernoulli distribution. So we have a Bernoulli distribution means that we have only two classes, 0 and 1, right? As we have seen often, and we have such data. So the first thing that we left open was the loss function. And most of the time, what we do for classification is we use, as we have also done before, we use cross entropy. And given that we know for each data point whether it's class 0 or 1, this amounts to looking at what is the expected value given our data sample of our netlog likelihood. And this is a kind of a special case, then the cross or the netlog likelihood is a special case of our cross entropy. I mean, whether we have here the correct class 0 or 1, this sort of is hidden here, but effectively then means that we just sum up our log likelihoods here. Now, again, still the same kind of test data, label data, and now we model our set by this linear modification of the input, and we model and say that let the logarithm of this probability be the same as the y times the set. That's just a decision to say that this probability is nothing else than this sigmoid function, where as input to the sigmoid function, it's y set. And well, of course, below we have to go over the two classes to normalize. And this, when is this term large? When this term above is large, then this goes against the probability of 1. It is large if y equals 1 and z is large, or otherwise not. If y equals 0, then this is 1 and this is some large term possibly. So that's not large, but if y equals 1 and z is large, then this will approximate 1. And we can look at these possibilities and describe the whole term. We can reformulate this for this specific case as being the same as e to the power 2y minus 1 times z divided by this normalization. Well, this is just writing down what's otherwise here. And this is the same as the sigmoid of this modified term. And if this is now our probability, some sigmoid, then the loss is the netlog likelihood, which is minus the logarithm of this term. And this is the zeta function of this term if we do the computation of how the two are related. Remember, the sigmoid function has all these exponentials which can be neutralized by the logarithm, so to say. The zeta function is logarithm of 1 plus e to the power x, And this zeta function looks like this green thing here. It's also called the soft plus, and looks like almost like a ReLU, but like a soft ReLU. So this is our loss function that we get out when we use, when we use then the cross entropy, and the derivation of this loss function when we want to do a gradient descent is again the sigmoid function. So these two are then very much interwoven. And logarithm of this. So there are a number of these relationships between this soft plus and the sigmoid function. And when we look at this loss function, again there is the question, when does this loss function saturate? What does saturate mean? You have to remember we have some function, and we try to find an optimum, minimal loss. And the question is, when do we find either at least a local optimum or even, well, global optimum would be here, but when do we find a good value for all our parameters in these different weight matrices? We find these by doing, from a certain point on, gradient descent. The question is, does our loss function give us a hint where to go? And it only gives us this hint if it's non-zero. If the loss function is 0, then there's no hint anymore. If the gradient is 0, there is no hint anymore. So here, of course, we would have no information anymore where to go, because the gradient would be 0. And so when the gradient, when this function saturates, it means it becomes 0. It does not give us any intuition anymore where to go and how to optimize our parameters. That is meant with saturate. So not providing guidance to the gradient. And when does it saturate? Well, it saturates if this term is very negative, which is either if y equals 1 and z is very positive, or y equals 0 and z is very negative. And both of these cases are the cases where we do the right thing. Because if we have this class and we have a very large input to our activation function, then this is a right thing to have. And if this is very negative and this is the class 0, then we are also correct. So the important observation here is that we saturate exactly when we do the right decision. So that comes out as a result of using cross entropy as a loss function, then looking at how does our gradient behave under this loss function. And this is what we always have to keep in mind when we try to define loss functions for a particular problem. When does it give us a hint where to go? And when it stops giving us hint because it becomes 0, are we in the right place? And this is the case here. We are in the right place when it stops giving us further hints, so when it saturates. So, to summarize, learning Bernoulli output means we model our prediction function as the sigmoid. This is the logistic regression, basically, you could say. We have as a loss function our soft plus, derived from the cross entropy, which saturates when we have the correct result. We solve with gradient descent, which is just the soft plus derive, which happens to be the sigmoid. Okay, that was now a super simple thing. But now let's do this with feed-forward networks for a multi-Nully distribution. For Bernoulli distribution, we have that y hat is the probability of y equals 1 given x. But, I mean, y hat represents here either class 0 or class 1. What do we do if with a multi-Nully, like the throwing of a dice, would be 6 different values? How do we decide there? For multi-Nully, what we have to do is we have to represent different values for each possible category that we can have. So if we have a dice, we need here 6 different values, y1, y2, up to y6, to represent each of the 6 different classes. And the overall vector would now be a vector of predicted values for these n different classes. Of course, before we said y hat was either 0 or 1 or in between. And now each entry is between 0 and 1, but the sum of these values must be 1, because when we want to have probabilities, the probabilities of all possible values must add up to 1. So the next consideration then is we have our weight matrix, we have our input, and what we get here are a vector of logits, and we put this into softmax. And the softmax, like with logistic regression, gives us then the probability distribution over these possible classes. So for Bernoulli, we had this set was this. Now, because we do not just have one output, we need a vector of outputs. Instead of a weight vector, we have a weight matrix. And we turn this set, which is a vector of values, into the softmax of set. And for a particular component of this vector softmax of set, the ith component, we compute this sigmoid-like function, but here we normalize by all the values of all the possible classes. So this softmax of set is a vector, but the ith component of it is of course a scalar. Here is a website where you can play around a bit to understand the softmax. So and here on this slide are a few examples. So here are different set values. The set values are somewhere on the real line between minus infinity and plus infinity. And here the value is -5, -1, 2, 5, 3, 2. And with a softmax, with taking the value e to the power of this value, and you go over all the combinations and add them up, you basically make the large numbers larger and the small numbers smaller, and you normalize that all the numbers fall between 0 and 1, and all the numbers add up to a probability distribution of 1. So for these numbers, the 3.2 receives a probability of 66%. The 2.5 is close, but I mean, this is a small difference, but this is a difference that's rather large between these two numbers. The others have hardly any probability mass assigned. Here, another example, 3.2 and 2.5 stays the same. This other stuff is changed a bit. almost stays the same probability mass distribution. Here we have some larger numbers, and you see most of the mass goes to the largest number. So you can say this softmax is not the winner takes all, but the winner takes most of the probability mass. That's what happens. Now, how do we model a loss function? For each data point, we have now a label y, and this label y is as long as we have many categories. So for a dice, we would have 6 components. And if for a dice, let's say I have the correct number would be 3, then on this position number 3, there would be a 1, and in all other positions, there would be a 0. Well, let's assume you label pictures. You label pictures with pictures with animal photos. Let's assume you have 10,000 possible animals, from ants to ducks to pigeons, etc. Then you would have a 10,000 vector for your y, and only in a single position it would say this is a pigeon by having a 1 there. This is basically a probability distribution over all possible values, and since you label this manually, you say the probability for this being a pigeon is 1. This is a so-called one-hot vector. One-hot because there's a 1 in one place, indicating this category which is hot, which is the correct one. All other places are 0. Instead of writing it in this inconvenient manner, we often just write y equals I. Well, y equals 3 means it is this vector with a 1 in the third position, all other components being 0. So when I now look at the loss, I model the true value, and in order to write it conveniently, I say this is a Kronecker function, and this is 1 if the condition is correct. So y of j equals I means is j the same value as the I. So I go over all the possible components of my vector for a single data point. So I go over all these positions here. And in case I have in the chase position the right one, then I take the logarithm of the softmax in this chase component. So that means 0 times anything, doesn't matter. But if I have the 1, I take the logarithm of the softmax of my set. So how much probability mass is assigned in this place? If all the probability mass is assigned here, then I have a 1. The logarithm of 1 is 0. I have no loss. If I have, let's say, only 50% here, softmax of set is in this component is 50, then I have here the logarithm of 0.5, which would be, when I take the binary logarithm, which would be -1, then I have 1 times -1 minus would be a loss of 1. And of course, I can write this more conveniently by just this way. All the others don't play a role. When I know that the ith position is here, the correct one, I can just write it like this. And this is nothing else by using the softmax definition than this. So this is here the loss that I get if I know that the I is the correct position, I is the correct class. And this I can simplify into subtracting the two logarithms. And this here, I can put this zi in front and I have the logarithm of e, which is 1. So this would be zi minus the logarithm of this. And now one thing I have to consider, what happens with my linear modifications? When I have a linear function, I learn linear parameters, I might end up with rather large values. And you could say it doesn't matter whether I have softmax 1, 2, 3 or softmax 1000, 2000, 3000. What happens, however, with softmax 1000, 2000, 3000? You put these values into the exponential. And then your whole numerical approach is not stable anymore. So what you then have to do is you have to avoid these large numbers in order to be numerically stable, but you can easily subtract. You have in the numerator and the denominator the same number, and if you use e to the power minus c, you can subtract and you can come up with a numerically stable result without computing an exponential of a very large number. So to summarize a multi-Nulli, softmax is a soft generalization of argmax. Argmax is a bit similar, give me the largest component. Winner takes most, and here's some further thing of the softmax function that you can look at, which I like better than the neural network book.